Hello, everyone, and welcome. On behalf of the Environmental Finance Center Network, welcome to the 12th session in our Operator Certification webinar series on modified treatment processes. My name is Kristen Crew from the Syracuse University Environmental Finance Center. Before we begin, we're going to go over a few logistics and then we can get started. During the webinar today, everyone will be kept on mute to ensure audio quality. If you have a question, please type it into the GoToWebinar question dialog box anytime throughout the session. We will be saving your questions for a facilitated Q&A session at the end of the presentation. After the webinar, you will receive a follow-up email that includes a link to the recording and other information that you may need. You're also able to download the slides from today in the Handouts tab in your GoToWebinar control panel. This webinar has not been submitted for pre-approval of continuing education credits, but eligible attendees will receive a certificate of attendance for their personal record. To receive a certificate for this session, you must attend for the entire session and register and attend individually using your real name and unique email address. Certificates will be sent via email within 30 days of the webinar date. If you have questions or need assistance, please contact smallsystems@syr.edu. Now for a little bit about us. The Environmental Finance Center Network provides training and technical assistance to small water and wastewater systems in all U.S. states and territories through our building technical, managerial, and finance capacity programs. If your community or utility needs assistance with drinking water or wastewater system management, please feel free to contact us through our request form, which I will be sharing shortly in the chat. On that note, we can get started. I would like to introduce our presenter for today, AJ Barney. AJ is a research engineer at the Southwest Environmental Finance Center. Welcome, AJ, and I will hand it over to you.
Okay, sorry about that. Okay, so after that quick glitch, so like I said, today I'm going to be presenting on modified treatment processes. And as Kristen mentioned, my name is AJ. I'm a research engineer with the Southwest Environmental Finance Center based out of the University of New Mexico. Just a little quick background about myself. I am a civil engineer and a biologist. I've been working in wastewater for about 10 years. And then I am also a New Mexico Environmental Department certified level 4 wastewater operator. Previously, I worked at the Albuquerque Water Authority as both an operator and in compliance. And now I've been with the Southwest Environmental Finance Center for almost a year. And before we get started on the presentation itself, I'm going to talk about a couple of opportunities I would like to promote in line with the other technical assistance information. So specifically, we are offering technical assistance for implementing pre-treatment programs. So if you've ever had any questions about like fog prevention, the EPA dental rule, or developing other aspects of pre-treatment, such as an industrial sampling program, we are currently looking for technical assistance opportunities. And if you have any questions about this kind of stuff, or it's been something you've been looking for, feel free to email me or also contact the EFCN website and go through the technical assistance submission. Another opportunity that we're talking about for technical assistance that we have available is a open office hour for wastewater technical assistance. Me and James Markham, another research engineer at the Southwest Environmental Finance Center, are available on Tuesdays from 11 to 12. And this can be anything from troubleshooting, operator certification, training, financials, fog, and other pre-treatment topics. So if you're interested in this kind of thing, feel free to email me or James or request through the website, and we can provide you the link to this, and we will be available for any of these types of questions, and we can be at your disposal. One last thing, I'm sure many of you have seen this before, But I wanted to mention that for operator certification, that this kind of thing is typically regulated through your environmental department for your state. So for Texas, this is the Texas Commission of Environmental Quality. For New Mexico, it's the New Mexico Environmental Department. In Oklahoma, we have the Oklahoma Department of Environmental Quality. Those are just a couple examples from Region 6. All of these offer different certification levels, and they're going to be based on a variety of factors. And they also offer different resources, such as study guides, need-to-know lists, and also one of my favorite is the California State University Sacramento Wastewater Operation Manual. Those are kind of the go-to standard for the industry. I'm sure many of you know. So I just want to point out that this webinar is designed to kind of give a good overview and provide you guys with the topics that you're going to become really familiar with for your certification exams. All right. With that being said, we're going to start our presentation about our modified treatment processes. Modified treatment processes refer to variations or adaptations of conventional wastewater treatment methods that have been modified to improve efficiency, enhance treatment capabilities, or address specific wastewater characteristics. These modifications can be made to various stages of the treatment process as well. So examples of this are membrane bioreactors, sequencing batch reactors, advanced oxidation processes, and even construction wetlands, which may be considered a modified treatment process. I accidentally included anaerobic digestion on there, but we will not be covering that. We're going to talk about construction wastelands instead. Let's see. And this webinar will mostly cover membrane bioreactors and sequencing batch reactors, but we will also briefly touch on advanced oxidation processes and construction wetlands. So with that being said, we're going to start with our membrane bioreactors. And so basically, a membrane bioreactor, or what we're going to call for the rest of the presentation, MBR, is a wastewater treatment process that combines the traditional or more widely used principles of biological treatment and newer membrane filtration technologies. So just like in typical biological wastewater treatment processes, the biological reactor provides an environment for microorganisms to break down and consume organic matter present in the wastewater. But the caveat is there's also a membrane filtration system, which is the key feature of the MBR that differentiates them from traditional wastewater treatment processes. This separates the treatment wastewater from the microorganisms and suspended solids, and it consists of a fine pore-sized membrane that acts as a physical barrier. So the membrane allows the passage of treated wastewater while retaining the suspended solids, bacteria, and other microorganisms within the reactor. The membrane effectively removes suspended solids, pathogens, and most of the dissolved contaminants from the treated water. So now that we've kind of mentioned just briefly what it is, we're going to talk about some of the advantages that MBR systems have. MBR systems have several advantages over conventional wastewater treatment methods, such as they produce high quality effluent that can be reused for a variety of purposes, such as irrigation or industrial processes. MBRs also have a smaller footprint compared to traditional treatment systems, since they eliminate the need for a separate clarifier or sedimentation tank. And they also allow for higher concentrations of microorganisms, reducing the size of the need for a bioreactor, or reducing the size of the needed bioreactor. The small footprint means they can be ideal for locations with spatial limitations. And additionally, MBRs are highly effective in removing suspended solids, pathogens, and nutrients, resulting in improved water quality. They can be operated at higher SRTs than other biological processes, with typical MLS concentrations of 8,000 to 12,000 milligrams per liter, and even as high as 15,000 to 25,000 milligrams per liter. So with those advantages, they also have a few issues and challenges that they need to overcome. The fouling of the membrane is the most typical one, and that's due to the accumulation of solids that reduces systems efficiency and require periodic cleaning. Fouling can be mitigated through a variety of strategies such as air scouring, backwashing, or chemical cleaning. So we'll go into that a little bit more later on in the presentation. And they also require regular maintenance and monitoring to ensure proper orientation. Fouling, maintenance, and monitoring can cause MBRs to be less cost effective than other wastewater treatment processes as well. Now we're going into a little more details about the MBR process, and there are usually about 8 steps in the MBR process, and we've laid them out here. So first, the wastewater to be treated is collected and transferred to the MBR system. The MBR can come from a variety of sources, like we talked about, such as municipal sewers or industrial processes. Next, just like in large-scale wastewater treatment plants, MBR wastewater treatment plant processes should include a pre-treatment process to protect plant equipment, especially membranes, which are highly susceptible to damage in the presence of high levels of debris. And these membranes are usually made from very fine materials. So smaller and medium-sized MBR plants may not always require pre-treatment, but they can provide the same benefits if the resources and space is available. Now, all MBR plants, however, do require fine screening before the membranes, and these screens require frequent cleaning. So the collected wastewater then enters the biological reactor after pre-treatment, which serves as a habitat for the microorganisms. And those microorganisms, which are typically bacteria, play a crucial role in the treatment process. They consume and break down organic matter present in the wastewater, metabolizing it into carbon dioxide, water, and biomass through processes like aerobic and anaerobic digestion, depending on the system design. So like many of you, I'm sure, are familiar with, those are our traditional biological processes. So the biological process in here is going to run on the same principle. So to ensure optimal conditions for the microorganisms, the wastewater is continuously mixed and aerated. Mixing helps distribute the microorganisms evenly throughout the reactor, ensures that all wastewater comes into contact with the biomass. Aeration provides oxygen to support aerobic microorganisms and facilitates the breakdown of organic matter. Then our fourth steps, so after the biological treatment, the treated wastewater containing microorganisms and suspended solids is then subjected to membrane filtration. The membrane is located within the biological reactor and acts as a physical barrier with fine pores. As the wastewater passes through the membrane, it filters out the suspended solids and microorganisms like we talked about. The treated water is collected and now ready for further treatment, use, or discharge. Now, our sixth step is that within the MBR system, the accumulation of biomass and solids on the membrane surface is referred to as sludge. And I'm sure lots of you are familiar with this topic because that's typically how it's referred to in wastewater. And this sludge needs to be managed to maintain system efficiency. Some MBR systems utilize a portion of the treated biomass within the reactor to maintain the biological treatment process, while excess biomass, known as waste-activated sludge, may be periodically removed. This practice is similar to what we frequently see in activated sludge processes, and the removed sludge can undergo further treatment process such as dewatering or digestion to reduce its volume and facilitate disposal or beneficial reuse. Typically, these processes are similar to what you would see at other facilities, and I would suggest revisiting our YouTube channel for our webinars covering solids handling for more in-depth look at solids handling. Now, another step, this is an optional step, but low levels of phosphorus and nitrogen and bacteria can be present in the MBR discharge, and depending on the specific plant permit requirements, these can go through traditional processes such as nitrification, denitrification, and disinfection to remove those. And our final step in an MBR is the one that occurs throughout the process is control and monitoring. MBR systems require regular monitoring and control to ensure optimal performance. And some of these parameters that are monitored may be dissolved oxygen levels, pH, and membrane fouling. And they can be adjusted to maintain efficient operation. So here is a diagram of the MBR process. And if you'll see, this looks very similar to other activated sludge processes where we'll have our pretreatment followed by our anoxic and oxic zones. But the difference is that you'll typically see an oxic zone with the membranes in it over here in the middle of the screen where it says aerobic plus seaweed, which is a brand that's provided by the EPA fact sheet. Then after that, you have your turbidity readings and your clean in place tank, which monitors the turbidity of the water to verify if it's being filtered correctly, and will actually rerun the water through the filters if needed. And this is a configuration for an integrated MBR. So now that we know about the overall process of MBR wastewater treatment, let's talk more in depth about the crucial role membranes play in the MBR systems. So like we said, they facilitate the separation of suspended solids, microorganisms, and other contaminants present in the wastewater. They act as a physical barrier and selectively allow the passage of water molecules while retaining the larger particles and microorganisms. So let's go over a couple steps of what exactly these do, because understanding membrane function is crucial to understanding our MBR. So the filtration process in MBRs occurs as the wastewater passes through the membranes. The wastewater contains suspended solids, microorganisms, and treated water like we talked about. And the treated water applies to one side while the contaminants are on the other. And I'm going to show you guys a diagram on the next section about how that occurs. The membranes are designed with pores of a specific size, depending on the desired filtration efficiency and the characteristics of the wastewater being treated. Membranes in MBRs employ a size exclusion mechanism to separate the particles and microorganisms from the treated water. The membrane pores are typically in the range of microfiltration to ultrafiltration. As the wastewater flows through the membrane, particles larger than the pore size are retained on the membrane surface or within the membrane structure. The treated water that passes through the membrane pores is referred to as permeate. It is collected on the opposite side of the membrane, separate from the concentrated sludge and suspended solids. The collected permeate is relatively free of contaminants and can be used for various purposes, such as reuse, discharge, or further treatment if necessary. Now, due to the small pore size, permeate does not naturally pass through the membrane without an outside force facilitating the passage of permeate across the membrane. And the driving force for membrane filtration in a membrane bioreactor is the pressure differential across the membrane. Another important characteristic of membrane is flux, which measures the rate at which permeate passes through the membrane. And this can be thought of as the filtration rate of the membrane. Now, membranes in MBRs are prone to fouling, which refers to the accumulation of solids and microorganisms on the membrane surface over time. Now, fouling can reduce the efficiency of the membrane and impact the overall performance of the MBR system. To mitigate fouling, various cleaning techniques are employed, such as physical methods, which includes air scouring and backwashing, and then chemical cleaning, which utilize specific cleaning agents to dissolve them. MBRs can also utilize different membrane configurations, including the type of material, which could be hollow fibers, tubular membranes, or flat sheets. And depending on the system, configurations of where they are in the system can also differ. And these configures also offer various advantages. It may differ in terms of the material, packing density, and the flow patterns. So here's a quick look at what a membrane looks like. As you can see, wastewater flows along the membrane surface and contaminants stay in the flow, while permeate flows through the pores and across the membrane to the permeate side. So this is typically what's happened on the left. You'll see particles will be in there. The water looks a little dirtier. And on the right, there'll be clean water. And also, if this is an immersed system, biological activity will be continuously going on the left side as well, breaking down organics. So we've touched on this previously, but I wanted to reiterate that there are two products that are created during membrane filtration. The first is permeate, which we've already described as the clean water product after the filtration process within the MBR. And permeate is the desired product of the MBR process, and quality of permeate dictates the design considerations and operation optimization of the MBR. Then the other product we want to know is concentrate. And the concentrate refers to the concentrated wastewater stream that remains after the membrane filtration process. It is also known as the reject stream or the retinate. The concentrate contains the majority of the solids, microorganisms, and dissolved contaminants that were present in the influent wastewater. In many cases, MBR systems may incorporate a concentrate recycle or reuse strategies. And this involves redirecting a portion of the concentrate stream back into the effluent wastewater to enhance treatment efficiency or reduce the overall volume of the concentrate generated. This approach requires careful consideration of the impact on the system, how much this may increase fouling, and potential contaminants in the recycled concentrate. So next we're going to talk about pressure. And as we mentioned, membrane filtration relies on pressure and the pressure differential across the membrane for the process to proceed. Now, there are two types of pressure differentials that may exist across an MBR membrane. There is the transmembrane pressure, or the TMP, and is created by applying a high pressure on the feed side of the membrane compared to the permeate side. And this pressure difference pushes the wastewater through the membrane, allowing clean water to pass through while retaining the solids and microorganisms. And it can be created in a variety of ways, including as a pump-driven system. So you'd have a pump pushing, and it's pushing the wastewater on the concentrate side, and then the clean water will force its way through the membrane to the permeate side. There are sensors placed on both sides of the membrane to monitor the pressure differential, to measure the pressure differential, and it's used to monitor for changes that indicate fouling or other issues in the system. Now, in addition to the transmembrane pressure, the hydraulic pressure generated by the flow of the wastewater can also contribute to the driving force for membrane filtration. As the wastewater flows across the membrane surface, the hydrostatic pressure helps propel the water through the membrane pores, facilitating the separation of the treated water from the solids and the microorganisms. And it's also worth noting that the pressure required for membrane filtration can vary depending on the membrane type, configuration, and the specific characteristics of the wastewater being treated. So as we mentioned earlier, flux is the rate at which the treated water passes through the membrane per unit area. And this is typically driven by the pressure, which we just talked about. Flux is typically expressed in terms of the volumetric flow rate per unit membrane area, such as liters per square meter per hour, which is shown here, or gallons per square foot per day, which is also referred to as GFD. And it represents the amount of permeate that can be produced or processed by the membrane in a given time. It's important to remember that MBRs generally operate at a flux between 10 and 150 LMH. It's very widely based on the system. Some things that influence flux are the transmembrane pressure, membrane characteristics, the fouling that's occurred in the system so far, and membrane integrity, so how well that system may be holding up. The relationship between fouling and flux is especially important, though, because increased fouling leads to a decrease in your flux rate. So, as we mentioned before, fouling is a frequent issue for MBRs. Like we said, decreases your fouling, your flux rate, and overall performance of your MBR. And here's just a couple examples of how this occurs. So fouling is caused by fine suspended solids in the influent wastewater that can deposit and accumulate on the surface of the membrane and within the pores. And they can include organic matter, colloids, bacteria, and other particles. So the first that we're going to talk about is biological growth, which is typically caused by microorganisms, including bacteria and biofilms that attach and grow on the membrane surface, leading to biofouling. The growth of microorganisms can result in the formation of a slimy layer that impedes the permeate flow. Then there is scaling, which occurs when dissolved organics compounds, when dissolved inorganic compounds in the wastewater. This can be like calcium carbonate or calcium phosphate, precipitate, and other forms of deposits on the membrane surface. Scaling can also reduce the effective pore size and decrease membrane permeability. And the last cause of fouling that we're going to talk about is organic fouling, where there are certain organic compounds in the wastewater, such as proteins, humic substances, or oils that can absorb onto the membrane surface, resulting in fouling. This absorption can occur due to electrostatic interactions or hydrophobic/hydrophilic interactions. Now, just a couple of things about how to treat fouling. To mitigate fouling in the MBR system, various strategies are employed, which include the regular cleaning of the membrane through physical methods such as backwashing and air scaling or chemical cleaning, which we mentioned earlier. And there's also membrane surface modification, where the surface of the membrane can be modified to enhance its anti-fouling properties, make it less prone to fouling by modifying the surface chemistry or incorporating specialized coatings. Then fouling can be mitigated by implementing appropriate pre-treatment processes, such as screening, grit removal, or coagulation, and can help reduce the load of suspended solids and certain fouling compounds in the influent wastewater, thereby minimizing the fouling potential. Finally, there's also operational parameter optimization, which is accomplished by adjusting operating parameters such as the transmembrane pressure, aeration rates, or solid retention time to minimize fouling. So there are a couple of different ways that membranes can be configured, and we're going to talk about those since we've kind of finished with principles. Membranes can be immersed directly into the bioreactor, as we saw earlier, or installed as a separate system following the biological process. In an immersed membrane bioreactor, the membranes are submerged directly into the mixed liquor within the biological reactor. The membranes are typically placed within the reactor as modules or bundles, and they are fully immersed in the wastewater. The mixed liquor flows over and around the membranes, and the filtration process occurs as the treated water passes through the membrane pores. In a separate membrane bioreactor, the membranes are physically separated from the biological reactor, and the mixed liquor from the biological reactor is transported to a separate filtration tank or module where the membranes are housed. The filtration tank is designed to create a pressure difference across the membranes and allows the treated water to pass through while retaining the solids and microorganisms. So here's a quick diagram of a external membrane system. So as you can see, this looks like a typical wastewater facility where you go through screening, and then you will go through your activated sludge process, such as anoxic, aeration, aerobic digester. And then the reuse quality effluent goes through the membrane operating system. So it'd be a separate membrane system where you can see the different modules in here. Those are the cylinders at the bottom within the membrane operating system, and water will flow into the big tank and catch onto the little pores. We saw this one earlier, but this is an example of the immersed membrane system. And as you can see, the biological process will be happening at the same time as filtration is occurring. So there are two common types of membranes used in the MBR system. There's microfiltration, which we mentioned earlier, and ultrafiltration. Microfiltration is referred to as MF and ultrafiltration as UF. Now, MF membranes have a larger pore size and provide relatively lower filtration efficiency, and the pore size is typically 0.01 to 0.4 micrometers. And while they have lower filtration efficiency, they do allow for the treatment of more water. While UF membranes have smaller pore sizes and offer a higher filtration efficiency, the pore size for UF membranes is 0.01 to 0.1 micrometers. And the choice of membranes type depends on the specific application and the level of treatment required that may be dictated by a plant's permit. So the most common type of MBR system utilize hollow fiber ultrafiltration membranes, and the second most common is the flat plate microfiltration membranes. Here's an example of the hollow fiber membranes. Water flows from the like we mentioned earlier, flows from the outside of the membranes to the inside in this type of membrane media, and that typically requires either an outside pressure pushing the water, or in these cases, it would be actually a vacuum system that attaches to the module which holds all the fibers. These fibers are about 1 to 3.5 millimeters, which is slightly wider than a regular strand of hair. And they come in, like I said, big tubes, which have thousands of them. And the water's pushed into the middle, and the permeate sucked through with like a vacuum system. So that's about what we're going to cover today for the basics of MBRs. And now we're going to move on to talk about our sequencing batch reactors. But before that, we have a couple of poll questions.
All right, first poll question. What does MBR stand for? Go ahead and get your answers in. I'll be closing this poll in 3, 2, 1. All right, AJ, looks like most people got the answer correct with B, membrane bioreactor. Next poll question, what is treated wastewater that passes through MBR's membrane called? Get those answers in. I will be closing the poll in 3, 2, 1. All right, most people got it right again with D, permeate. 79% of them did.
Good job. So if you remember, concentrate is the opposite or the counterpart to permeate, and then influent is typically your raw water that comes in. And to be drinking water, there would probably be a lot more process that would be needed.
All right, and then the third poll question, an MBR utilizes membrane fibers with a pore size of 0.3 micrometers. What type of membrane does this system most likely use? Get those answers in. I'll be closing the poll in 3, 2, 1. All right, and again, most people were right with C, microfiltration. 70% of them were.
Good job, guys. So we didn't really cover nanofiltration, but that's actually going to be even smaller than ultrafiltration. But if you remember, microfiltration, the size is between 0.01 and 0.4 micrometers, and ultra is 0.01 to 0.1. So it would fall in that microfiltration rate. And coarse filtration is typically like sand filtration and stuff like that. All right, with that, we're going to go on to, like we said, we're going to our sequencing batch reactors. Okay, so I'd like to mention that this section will be a little shorter, or it's shorter than the MBR section, and it's because it's important to understand the configuration and sequence difference that SBRs have from traditional processes. but the principles in chemistry are going to be the same that we've discussed in previous webinars. And actually, we plan on going into more detail in the future for biological processes, specifically activated sludge. So sequencing batch reactors, or SBR systems, are a type of biological wastewater treatment system, like we said, and they're commonly used in small to medium-sized wastewater treatment plants, as well as decentralized and industrial applications. So SBR systems operate on a batch process similar to a fill and draw systems, which were first developed between 1914 and 1920. And in this batch process, wastewater is treated in discrete batches rather than continuously. The treatment process consists of several phases that occur sequentially in a single tank during a single cycle. So typically, SPR systems use 2 or more batch reactors in tandem to maximize efficiency, create redundancy, and allow flow to be continuous throughout the plant. Now, the EPA has determined that SBRs and activated sludge systems are essentially the same thing, but that SBR operates in time rather than in space. And I'll go into why that is. So here's a quick overview of the SBR wastewater system. And this is why it operates in time, because all this is occurring in one single place, whereas in most facilities, these processes are typically broken up in different processes and occur sequentially as it moves through the plant. So the typical first step in an SBR plant is to remove debris and grit, just like we would in the MBR or traditional wastewater treatment plant. And then next, after the water has been all the trash and debris has been removed, it is time to fill the SBR tank with the influent wastewater. The SBR tank is kept partially filled with the desired biomass as a way to seed the bioreactor, and the influent wastewater to be treated is introduced to the partially filled tank. The influent wastewater is controlled to achieve a desired flow rate and hydraulics retention time. Now, once the tank is filled, the aeration phase begins, and oxygen is supplied to the tank to provide mixing and to create an aerobic environment, which promotes the growth of microorganisms that consume organic matter and pollutants in the wastewater. And after the aeration phase and biological reactions are complete, the aeration and mixing is discontinued and the wastewater is allowed to settle. During this phase, the suspended solids and biomass in the wastewater settle to the bottom of the tank due to gravity. And that's just like we would see in like a primary or secondary clarifier. Once the settling phase is complete, the clarifier water at the top of the tank is allowed to decant or is withdrawn from the system. And this decanting process is carefully controlled to avoid disturbing the settled solids at the bottom. Now, depending on the system, this may be 75% of that water, so you leave enough of the the water that's stable to continue the cycle, or 50%, but it's all system specific. After decanting, the tank is left idle for a specific period, allowing any remaining solids to settle further and prepare the tank for the next cycle. And this is also the period where some solids might actually be removed as well. So here's a diagram of the typical SBR system design. You can see the pre-treatment before the SBR, and there's typically only one sludge that proceeds through sludge handling, and there's no need for settling after the SBR process, like you would see in activated sludge or other biological processes. There's sometimes an equalization tank, which is utilized before the effluent wastewater proceeds to filtrate, or I'm sorry, before the wastewater proceeds to filtration or disinfection. And this is to control for those two processes to make sure they are getting even flows. Then there's also filtration is utilized in the plant that if it needs to remove additional solids, and then disinfection is used to kill off microorganisms. So here's your typical design parameters for the conventional load through an SBR. These parameters are monitored and controlled to ensure effective and efficient treatment of the wastewater. So as you can see, there's an FGM ratio of 0.15 to 0.4 per day. For reference, typical FCM ratios in an activated sludge is 0.25 to 0.5. The detention time of an SBR is about 4 hours, while in an aeration basin it may be 4 to 8 hours, and it doesn't include the time through primary clarifiers, secondary clarifiers. So an SBR typically has lower detention times. The MOSS for a SBR is typically 2,000 to 2,500, while in activated sludge, you might see 1,000 to 4,000 milligrams per liter, and it's typically even closer from what I've seen to like the 4,000. So activated sludge operates at a higher MOSS. There's also the hydraulic retention time, which is related to the treatment cycle. So it's about 6 to 14 hours, while in an activated sludge plant, you might see 5 to 36 hours. So the average time is going to be longer for activated sludge. Here's a couple quick parameters operators should understand about the SBR. It should be noted that some of these seem rather obvious, but the actual value of the parameter is usually dictated by the manufacturer and the requirements of the system. And when I say obvious, I just mean like the naming convention. So the first is fill time, which refers to the duration of the filling phase in SBR. It's important to control the fill time to achieve consistent hydraulic retention time and influent flow rate. The fill time can be adjusted based on the influent characteristics, treatment goals, and the desired process performance. Then we also have the aeration time, which is the period during which the wastewater is aerated in the SBR, and the duration of the aeration time affects the efficiency of treatment and the level of oxygen available for microbial activity. Then there's settling time, which is the duration allotted for the settling phase in an SBR. Sufficient settling time ensures effective separation of the solids from the treated water and improves the effluent quality. Then there's decant time, which refers to the duration of the decanting phase in an SBR. And proper control of decant time is necessary to avoid disturbing settling solids and excess loss of biomass in the effluent. So this is just like in a clarifier where you want to make sure it's consistent so you don't create something like short circuiting. Also, we have the idle time, that is the period between decanting and the initiation of the next batch cycle. Idle time allows additional settling of solids, biomass growth, and the preparation of the SBR for the subsequent batch. Adequate idle time helps maintain process stability and optimizes the treatment efficiency. So now that we understand how SBRs work and the operation principles, we're going to move on to our next advanced treatment process called advanced oxidation processes. And just to mention real quick, these next two sections will be covered fairly briefly because they're not frequently topics on the operation certification exams. But I did want to give you guys an idea of what might be out there. And if you do know that this happens to pop up, it might give you just a good overview where you can know what topics to really reach into when studying. So the first is advanced oxidation process, or AOPs, which are a group of chemical treatment techniques used to remove organic and inorganic pollutants from water and air. AOPs involve the generation of highly reactive hydroxyl radicals or other powerful oxidizing agents, which are capable of degrading a wide range of pollutants that are resistant to conventional treatment methods. So the main principle behind AOPs is the generation of these highly reactive species, which can oxidize and break down organic and inorganic compounds into smaller, less harmful molecules. So the hydroxyl radicals generated during AOPs have an extremely high oxidation potential and can react with a wide variety of contaminants, including persistent organic pollutants, pharmaceuticals, persistents, industrial chemicals, and dyes. Some common AOPs are ozone-based processes, which use ozone either exclusively or in combination with hydrogen peroxide and ultraviolet light. Ozone is a powerful oxidizing agent and can degrade various organic compounds through direct oxidation or the generation, like we talked about, of hydroxyl radicals, which occurs when ozone mixes with water. There are also Fenton's agents, which are iron derived, or ferric derived, and they utilize a combination of hydrogen peroxide and ferrous ions under acidic conditions. There's also photochemical process, which involve the use of ultraviolet light, which either alone or in combination with hydrogen peroxide create those oxidizing agents that we're looking for. Fins agents and photochemical processes both generate hydroxyl radicals, which degrade, like we said, a wide range of organic contaminants. Lastly, there's electrochemical processes, which, like they sound, use electricity to produce species that oxidize pollutants as well. These are an emerging technology, and they're very useful that they may help treat the emerging contaminants that we're usually so concerned with. So here's a diagram of an AOP. And as you can see, the process follows typical wastewater processes with the addition of the ozone instead of oxygen. Now, ozone breaks down persistent contaminants, and as it reacts with these, or it reacts with water, it is converted to oxygen. And then oxygen just acts as it normally would in an activated sludge and nitrifies bacteria to convert ammonia, or nitrify bacteria that use the oxygen to convert ammonia to nitrate. So here's a quick pros and cons list. So AOPs are provide effective removal of pollutants, such as the normal pollutants that we would usually take care of, but also persistent chemicals. They have a broad spectrum of treatment, which include pharmaceuticals and personal care products, pesticides, dyes, and other industrial chemicals that you're not going to typically see in your traditional wastewater treatment. There is also a lot of environmental compatibility because they produce free radicals which exist normally in the environment. They also exhibit really high treatment efficiencies and removal efficiencies. Now, some of the cons is that they can be energy intensive because you're including the addition of these other options such as UV light or ozone, which takes a lot of power to generate. This increases the cost, which is also affected by the additional chemicals that you might need. And there can also be possible harmful byproducts that can be created. I'm sure a lot of us have heard of disinfection byproducts, and you got to be careful with these to make sure those are not produced. But as long as those aren't produced, all the byproducts that we see are stuff like hydroxyls, like we talked about. And there can be limited scaling abilities. So these are not always useful for large scale use, or it cannot always be expanded out for that. So lastly, we're going to go ahead and talk about construction wetlands. This is going to be our final kind of modified treatment process that we're going to talk about. Now, constructed wetlands are also known as artificial or engineered wetlands and are human-made systems designed to replicate the natural function of wetlands. It's kind of like the same idea as lagoons. People saw how slump conditions work. The same thing as people observed how wetlands treated wastewater, or when contaminants came through, how they were able to remove pollutants and stuff from the water itself. They are typically constructed using a combination of soil, gravel, plants, and various layers of materials to create a treatment system for wastewater. And the purpose of constructing wetlands is to treat and purify the water, removing pollutants and improving its quality before it is discharged into the environment or reused for irrigation. They're used in both rural and urban settings and can be applied to different types of wastewater, including domestic, industrial effluents, and agricultural runoff. Construction wetlands typically have three basic functions. First, they physically filter the water. As water flows through the wetlands, suspended particles and sediments settle down due to the presence of vegetation, gravel, and soil layers. And these layers act as a filtration system to trap the suspended particles. Secondly, wetland plants and microorganisms present in the soil and root zone of the plants break down and remove organic pollutants, such as nitrogen, phosphorus compounds. And they do this through assimilation, nitrification, denitrification, and the microbes in the soil decompose them. Lastly, there is adsorption and ion exchange. So some of the pollutants can be absorbed onto the surface of the wetland substrate or exchanged with ions present in the soil, reducing their concentration in the wastewater, or just water at this point. Now, construction wetlands offer a low energy option with minimal chemical use and the ability to integrate with the natural landscape. It should be noted that construction wetlands must be carefully designed and cannot be applied to all systems. So here's just a quick diagram of the wetlands. As you can see, wastewater is going to flow in to just what appears to be natural wetland plants and soil. And they're going to proceed in the direction towards the end of the treatment. There's able to be water control, and then you have an impermeable liner, so water doesn't infiltrate past the wetlands. And then the roots and gravel in there perform the actual treatment. So some quick pros and cons. In summary, construction wetlands provide effective water treatment. Like we said, they're good at removing nutrients, breaking down organic matter, and removing suspended solids. They're also cost effective because they don't need a lot of energy inputs or additional chemicals. They add to sustainability and ecological benefits since they promote biodiversity and create wildlife habitats. They also provide the aesthetic value since they're much better to look at than other wastewater processes, and can even offer areas for viewing wildlife and educational areas. And they also offer versatility and adaptability because they can be tailored specifically to the environment that they're in, the treatment needs, and the site conditions. Now, some of the cons are that they have large land requirements and may not be suitable for densely populated areas. And they have a long startup time, which can take several months or even years to get up to suitable treatment standards. They have specific design and maintenance requirements that must be carefully planned for. And we did mention that in the first slide. They are also affected by climate and seasonal variation and can break down in extreme weather, or can be overloaded during high precipitation events, or can even start to die off during drought events. They have limited capabilities to treat certain pollutants, such as man-made chemicals that we talked about for like the AOPs. So that is going to be the end of the presentation. Now, do we have any questions in the chat, or does anyone want to type anything in the chat that they were curious about?
Hi, AJ. Yes, so we do have a couple of questions. The first one is, could you please elaborate on the environmental compatibility as a pro of AOP?
Yeah, so typically the strategy for AOPs is to just create like ozone or hydroxyl. Maybe I could include a slide about that. But hydroxyl is basically just an oxygen and a hydrogen molecule, which is part of, like many of you know, water. Or ozone is just going to be 3 oxygen molecules combined. And they're very reactive, and they tend to just react with the contaminant, pull off a hydrogen molecule so they become less harmful, or it degrades them, and they start to break down, forming smaller, less harmful contaminants. So you might see things such as water being formed, or like I said, if it's like a complex biological organic, it's going to pull off a bunch of hydrogen molecules or form like hydroxyl groups on there that tend to make the whole thing break down. Then they become smaller constituents that are less harmful to the environment.
Perfect. And then the next question wants to know what the difference between adsorption and absorption is.
Yes, that frequently comes up. So adsorption is what we actually typically see. This is when a substance will, specifically like a liquid or something like that, will adhere to a surface and becomes attached to something. A good example of this is like a sponge. Now a sponge, you'll it's dry, you'll squeeze it out, and you'll put it in the water, and it's going to pull in all the water, and it's going to stick to like the surface of the different pores in the water, but it's not actually part of the sponge, and you can squeeze it out. Absorption, which is what we actually, the word that I hear most often, is actually the process that occurs less. And that's when actually something becomes integrated into a surface. An example would be there are some membranes that, or when membranes degrade, a lot of times it's because chemicals start to become integrated and actually part of the material. Yes. Try to think there's a little more I can say about that. But adsorption is more of a physical attachment to like a surface, but it, you know, it feels like it's becoming part of it. Where absorption is actually chemical integration, where it actually the substances become mixed together.
Perfect. And make sure that you get your questions in if you have any. I see one more right now, AJ. What is the popularity of new systems or modifications deployed in comparison to another SBR to MBR to AOP to artificial wetlands?
I think it depends on the size of the system. I think for smaller systems, we're starting to see more of the SBRs and the MBRs, especially the SBRs. We see that design a lot in package plants. Larger facilities, it's a little slower. Typically, you're still going to see your activated sludge, your aeration, and stuff like that. But I do, from what I've seen out in the field, the smaller application usually sees these modified treatment processes, whereas larger scale, a lot of times they're still using the large scale or the like the activated sludge traditional processes because those are better suited to treat large volumes of wastewater. However, with the increase in like emerging contaminants and stricter permit requirements, you know, stuff we're seeing for like mercury and personal care products and pharmaceuticals or PCPs, also, yeah, PFAs and like microplastics and stuff. I do think that they are going to lean more on these modified treatment processes to address those type of pollutants that are in the wastewater.
All right, a huge thank you to you, AJ, for sharing your expertise with us today. Following this webinar, each of you will receive a follow-up email with the slides from today, as well as a link to the recording. We also ask that you complete the webinar evaluation following this webinar, so you can let us know your thoughts on today's session, as this helps us plan future webinars on topics that are important to you. Thank you again, everyone, and we hope to see you at future EFCN events.
Thanks a lot, guys. Appreciate the questions. You guys have a great day.